Right, let's get started then. We're looking at the nuclear physics today for G485. So I'll start off with that as requested by you guys. And next one I'm planning to do electric fields, magnetic fields and capacitors. I'm hoping to do that Wednesday or Thursday. And I'll put it up on the calendar which one it will be, okay? So keep an eye on that today and tomorrow. It just depends how close I get to getting the presentation done. And then next week I'll do cosmology and probably medical physics all in one, okay? Alright, that's a picture of one of the laser preamplifiers at the National Ignition Facility where they're trying to achieve fusion on an economical scale. Right, so let's start off then. And we start off by looking at the alpha scattering experiment. That was, oops, let's go back. This is J.J. Thomson here, one of the English physicists. And he had come up with a model of the atom called the plum pudding model, where you had everything in like a solid mass. So the atom was just a solid mass. You've got all your positive charges and where it's generally positively charged, and then you had the negative charges embedded into that. And the alpha scattering experiment, which was conducted by Rutherford, who was actually who was working for J.J. Thomson. He was investigating what you could get out of atoms if you smashed energetic particles into them to break up the atom. What would you get out? And so what he was using were alpha particles, which are positively charged. And as he was investigating this, he had some surprising findings. This is what his setup was. He had an alpha source over here. The experiment takes place in a vacuum because alpha particles don't travel very far in air. So you need to get rid of the air so that they can travel far. He was targeting a very thin gold foil. So the idea was the alpha particles would crash into the gold atoms, break them up, and you'd be able to see what came out, or detect what came out. Surrounding this setup, there's a zinc sulfide screen, which is a scintillating material. So whenever ionizing radiation strikes the screen, you get a little flash of light. And so, because it's a very tiny flash of light, they were using a microscopic viewer to view at different positions around the gold foil to see what scintillations you could see at different places. And what he found was that most of the alpha particles, rather than smashing up the gold atoms, were actually going straight through. He's getting lots of scintillations over there. On the left, you can see by these particle paths here, there's lots of scintillation over here. So what he found, as I said, was that most alpha particles pass straight through the foil with just a small deflection. And then that 1 in 8,000 experienced a very large deflection or were scattered backwards. So you've got some going almost back towards where they came from. Some would be detected over here as well. Most of them go straight through, and just like very few were scattered backwards. So from this experiment, he was able to deduce a few things. Firstly, the atom is mostly empty space, and that's how most of the alpha particles were able to go straight through the gold foil. You know, gold foil looks very solid. You expect the alpha particles to be breaking up the gold into tiny little pieces, but actually most of that is empty space, and that's what enabled the alpha particles to go straight through. Nearly all of the atom's mass is concentrated into just a tiny nucleus. So you've got all this empty space and then a tiny, tiny, tiny little nucleus there. So that's what he called it, it's the atomic nucleus. And that nucleus is positively charged. I noticed earlier that alpha particles are positively charged. So the way that the alpha particles that were backscattered is because they were experiencing a large electrostatic repulsion from these tiny nuclei, and because the nuclei are tiny, therefore it's very rare that an alpha particle would actually interact strongly with the nucleus. But so they were bouncing back because of this electrostatic repulsion. So yeah, the nucleus is tiny and it's positively charged. To give you an idea of the order of magnitude we're talking about here, imagine a football stadium representing the space occupied by the atom, and in the middle of the football field you have a grain of sand. That's the kind of order of magnitude we're talking about. So nucleons, protons and neutrons, they're about 10 to the minus 15 meters, whereas the atom is 10 to the minus 10 meters. Okay? Right, particles. Since Rutherford's initial investigations, and Rutherford is often referred to as the first particle physicist because he started to find out about the structure of the atom in a new way. We've discovered a lot more particles since then, and this is the often called the particle zoo. We've got quarks, we've got up, charm, top, down, strange, bottom, quarks. And so we've got these quarks. By the way, what I'm talking about here is the basis of the standard model, what's called the standard model in physics, like the model for understanding nature and how everything is made up. So we've got quarks. There are 6 types of quarks. There are 6 types of leptons. I should also note, you don't have to know all of these. I'll point out the ones you do need to know, but I'm just sort of giving you a bit of familiarity with the standard model. Electrons, muons, tauns. Then we've got these different types of neutrinos. We've got electron neutrinos, muon neutrinos, and tau neutrinos. Then we have gauge bosons, and after the gauge bosons we have the recently discovered Higgs boson as well. So that's a type of boson too. They have various properties. Here, particle physicists will often talk about the key properties being mass, charge and spin. Okay, spin is something we don't actually cover. And all of these have antiparticles, okay, which are particles of the same mass, same properties, except they have opposite charge. And if they have a baryon number, they also have opposite baryon number as well. Okay, anyway, as I said, you don't need to know all of these. These are the ones you do need to know. And what I've introduced here are the antiparticles you also need to know about for OCR physics. So these are fundamental particles that you need to know. They are fundamental as far as we know at present. That may change because as higher energy experiments are conducted in places like the Large Hadron Collider, then new things are found out about existing particles, but also you may come across new particles that make up these. Anyway, as far as we know, these are fundamentals. So we've got, and the properties that you particularly need to think of are charge, baryon number, and strangeness. Quarks, we've got up, down, strange. Up has a charge of 2/3, baryon number of 1/3, and a strangeness of 0. Down has minus 1/3 charge, 1/3 baryon number, 0 strangeness, and then the strange has minus 1/3 charge, 1/3 baryon number, and a strangeness of -1. Then we've got leptons that you need to know, which are the electron and the electron neutrino. The electron has a charge of -1, no baryon number, it's not a baryon, and strangeness of 0, and the electron neutrino 0, 0, 0 for all those. This is representing a photon, by the way, which is a boson, and it's not a quark or a lepton. These are the antiparticles corresponding to these particles. Note that there is no antiphoton. Photons don't have mass, they don't have charge either, so there's not an antiparticle for photons. Anyway, so you've got the anti-up, anti-down, anti-strange. This is a positron, which is the antiparticle of the electron, and the anti-electron neutrino. The charge and baryon number and the strangeness are negatives of their counterparts, okay, but they would have the same mass. So, for example, the anti-down has plus a third, and minus a third, and zeros, which you can see is the opposite of those. Okay. If you have any questions at any point, then do ask. Yeah.
You know how I said the photon doesn't have any mass, so it doesn't have any antiparticle.
Yeah.
The neutrino doesn't have any mass, but why does it have antiparticle?
Good point. I'm not saying that. Well, there are other properties as well, in addition to these. I couldn't say just on the basis of the mass and the charge, but photons don't have opposites. I can't remember. I think it is to do with the fact that they're massless. These, we're not sure if they're actually massless.
It's to do with lepton number something, isn't it?
What's that? Yeah. Well, the photons are not leptons, and leptons there are antiparticles. Yeah. So that's true. Were you going to ask a question? No? Okay. So you need to know that also that this basic quark model, remember I did show you there were 6, you need to know that although you only need to know about these quarks and these antiquarks, you do need to know it can be extended to include things like charm, top and bottom. Okay? They all, like the charm and top have similar properties to the up, except they have larger mass, and the bottom one has similar properties to down and strange, but it's got larger mass. Okay. You don't need to know how they're categorised, but you just need to know they can be extended to include those 6 quarks. Okay, hadrons, non-fundamental particles that consist of quarks. Baryons have 3 quarks. You need to know about some of these baryons. So, for example, a proton is baryon, and it has 2 ups and 1 down quark. Now, if you add up, because they combine to form a new particle, their properties are added together. So we've got 2/3 plus 2/3 minus a third. That gives us a charge of +1. So protons have a charge of +1 for that reason. Baryon numbers all a third gives you a baryon number of 1. Hence, protons are baryon, and strangeness is 0 for a proton as well, because all of those quarks have 0 strangeness. This is the antiproton. So if you take the antiparticles to these particles, so anti-up, anti-up, anti-down, then you get an antiproton, and you can see that all of those properties add up to a -1, -1, 0. Then we have the neutron, another baryon. This is made from an up and 2 downs, and the anti-neutron is an anti-up and 2 anti-downs. And you can see that we're getting, so it's got 0 charge, so you can't have an opposite, that's still 0, but the baryon number is 1, so that would be -1 there. Okay, so those are fundamental particles, and then some non-fundamental particles. You can see how the other particles are made out of those. Okay? Any questions about those? Right, let's look at nuclear radiation then. There are 4 types of radiation that are emitted by radioactive decay, so let's look at each one. Firstly, we have alpha radiation. The nature is that alpha particles are helium nuclei, so we're talking about a particle here. The charge +2 times the elementary charge. So the elementary charge, 1.6 times 10 to the -19 coulombs. It's positively charged, so it's plus, and there's 2 protons, so we've got 2 of them. Range in there about 10 centimetres, so very, very short range. If I had an alpha source here, it wouldn't be able to reach you. That's because it interacts strongly with air molecules. Penetration, just need a thin sheet of foil to block alpha radiation. So a thin sheet of aluminium foil, thin sheet of paper, that would block it. Because of this charge, it's extremely ionising. So if you look at the biological effects, alpha radiation inside the body is the most harmful, but outside of the body, because its penetration is so poor, it won't actually do much damage outside of the body. You can get radiation burns on your skin though, if it's very, very close. Beta minus, the nature of this is that the particles are energetic electrons. The charges are minus, is the negative elementary charge. These will travel about a metre in air. They interact with air molecules and fairly strongly, but not nearly as strongly as the alpha particles, which are much larger and have much larger charge as well. To block this, you'll need a few millimetres of aluminium to successfully block it all. Related to beta minus is beta plus. These are energetic positrons, plus E, so it's plus 1.6 times 10 to the minus 19 as opposed to being a negative. Same penetrating capabilities, so they travel about the same distance in there. These are matter and these are antimatter. Gamma radiation, gamma rays, so that's electromagnetic radiation. Charge, no charge, and it obeys an inverse square law with distance. So it will travel through air and the intensity of it will decrease. So if you double the distance, the intensity will fall to a quarter of the initial value. The way that these, alpha particles, they can strip electrons off of atoms, and if those atoms are in cells and bonded to organic molecules, you can wreak havoc with organic molecules, and even with water as well. You can form hydrogen peroxide and so on in the body. So these, because it's positively charged, it can strip electrons off. Gamma rays, if a gamma photon interacts with an electron, it can give its energy to an atomic electron, enabling it to escape from the atom. You'll need several centimetres of lead to successfully block gamma radiation. Let's look at these radiations in an electric field, because you can use the electric field to identify what type of radiation you have. So that gives you another method in addition to the penetration capabilities to investigate what radiation you have. So starting off with alpha. Alpha is positively charged, so it will deflect towards the negative plate. It's also very massive, so it will take a while to get significant deflection there. Beta minus is negatively charged, it deflects towards the positive. It's lighter, less mass than the alpha, so it deflects faster. Beta plus will deflect about at the same rate, but it's positively charged, so it goes the other way. Then you have gamma, which is undeflected in an electric field because it's not charged. And the way that you could check these paths is by using something like a cloud chamber. Right, radioactive transformations. If you have radioactive decay occurring, it's due to nuclear instability. So the atomic nuclei are unstable, and so in order to become more stable, a nuclide will undergo radioactive decay. Radioactive decay is random, so you can't predict when it's going to happen, and it's spontaneous. You can't cause it to happen as well. You can't change physical properties of the material to cause it to happen either. All of the radioactive emissions come from the nucleus. So if you get beta minus, those are electrons, but those electrons did not come from the orbital electrons of the unstable nuclide. They came from the nucleus. Okay, so all these come from the nucleus. Whenever you have decay occur, then the nucleon number, which is A, and the atomic number, Z, are conserved. So if we take our unstable nuclide here, this is the stable daughter nuclide that it transforms into, and then this would be your radiation, perhaps. Then you may have other particles. Okay, so we're just dealing with a simple case where you've got one and then another. During this transformation, the A number needs to be conserved, and the Z number needs to be conserved. So A1 plus A2 must equal A, and Z1 plus Z2 must equal Z. Alright? Now, the nucleons are protons and neutrons, so A tells you how many protons and neutrons are in the nucleus. Z, the atomic number, tells you how many protons there are. So if you want to know how many neutrons, do A minus Z, or A2 minus Z2, for example. That will tell you how many neutrons you have in each nucleus. Right, so let's look at the general equations for each type of radiation. Firstly, we've got alpha particles. They're helium nuclei, and the alpha particle is written like this, so alpha symbol, and then A number is 4 because it's a helium nucleus, right? So it's got 2 protons and 2 neutrons there. And then the Z number is 2 because it's got 2 protons. So if we start off with our general unstable nuclide, which is X, with A and Z, then that will decay into the element with a proton number 2 less than Z, and the A number will become minus 4 less, and then we've got the A. So if we do A minus 4 plus 4, it gives us A, and Z minus 2 plus 2 gives us Z. Okay, so that's alpha. Beta minus, those are electrons. This is written with a beta and minus 1. Because it's not a nucleon, it's not a proton or a neutron, then it has an A number of 0. So this is, the Z number is based on the charge. Starting off with X, then we've got Z plus 1 there, minus 1. There's no change in the A number. Okay. And then during beta minus decay, you have an anti-electron neutrino emitted, which has A0 and Z0. Because this Z plus 1, but A stayed the same, then what happened here is the new nuclide gained a proton. Okay. Next, beta plus particles. They're positrons, so this is 0 and plus 1. During this decay, we get a Z minus 1 there, and we've got this is an antimatter particle, so this is the matter neutrino, so it's neutrino, which is 0, 0. Okay. So although this is not changing the A or the Z numbers, because it's emitted, we have to write them down there. All right. And then we've got gamma photons, 0, 0. The star here, the asterisk, indicates that the nucleus has got too much energy. It needs to lose energy in order to become more stable. So effectively, the asterisk turns into the gamma photon. Okay, there's no change to the A or the Z number. No nucleons were lost or gained. Okay. Often what you'll find is that gamma decay happens in addition to something like alpha decay. So you have an alpha particle emitted from the nucleus, and the nuclide that's resulted from that decay has got some excess energy due to that radioactive decay, so it will then emit gamma photons. Right, so why do beta minus and beta plus decays occur? They occur because of this thing called the weak interaction. So, or the weak force. What this force can do is it can change one type of quark into another type of quark. And the weak interaction is one of the fundamental forces of nature. And the effects of this force only happen within nucleons. Okay, so remember, within the proton, you have 3 quarks. Within the neutron, you have 3 quarks, and this weak interaction is changing the quarks. So it only happens on that scale within that scale. So beta minus, we've already seen we have that kind of decay. So a neutron has turned into a proton, and the reason for that is that the weak interaction has caused a down quark to turn into an up quark. So if we look at what happened at the nucleon level, a neutron turned into a proton, plus beta minus, plus our antineutrino. And at the quark level, so this is like the fundamental level, a down quark turned into an up quark, and a beta minus and an antineutrino. Okay, so those are 3 equations to show you. This is what happened at like the atomic level. We're looking at what happened. This atom turned into this atom, okay, plus those. And this is the nucleon level, and that's the fundamental level. Fundamental, as I said, as far as we know. Beta plus, we have that kind of decay. So a proton turned into a neutron, and that was because an up quark turned into a down quark. So that's why it happened. So a proton turns into a neutron plus that, and up turned into a down plus a positron plus a neutrino. And if you were to look at all of the charge and other properties, you'd see that in each of those equations, so charge is conserved here, charge is conserved here, charge is conserved here, and charge is conserved in all of these. So all of the important properties that must be conserved are conserved in whichever reaction you look at. Alright, so how do we measure radioactivity then? We can use Geiger-Müller tubes to detect ionization events. So all these radiations, they can ionize atoms. So the Geiger-Müller tube can measure those events. So if you detect with the Geiger-Müller tube, that corresponds to 1 radioactive decay. That means that the count rate is your activity. The amount of counts you get on your tube, that's the activity, assuming that all of the decays cause an ionization event in the tube, which is not necessarily going to be true, but that's what we're assuming. And whenever you're taking measurements, you need to account for the background activity. And the background radiation is naturally occurring, random radioactive behaviour that's always present in our environment. And you get a random pattern from this, okay? So it's not like it's just the 1 every 30 seconds or something like that. It's a random pattern, okay? And if you want to have something measurable, you need to have something you can distinguish from that random pattern of radioactive decay. This is the makeup of background radiation. So we've got, this is what a typical person might experience in their life. You've got 50% is radioactive gases in the home. Nuclear power and weapons, about 0.3%. Grounded buildings, 14%. So, like the building materials used to make buildings, they contain radioactive isotopes, not very much. Medical uses of radioactive materials like radioactive traces and so on. Then your food also will contain a little bit of radiation. Cosmic rays, so the Earth's atmosphere is being constantly bombarded by energetic particles, causing cascades of radioactive behaviour. And then there are other sources as well, very small amount. So if you are taking measurements, as I said, if you have a very, very low activity, then it will be indistinguishable from the background radiation, and therefore you can't really take any reliable measurements from that. So let's look at how we can quantify radioactive decay. We use probability to quantify radioactive decay. Lambda is the decay constant, and that has units of seconds to the -1. That tells you the probability of a nucleus decaying per unit time. So for example, if you had a die and you were looking to roll a 6, and if rolling a 6 corresponded to a radioactive decay occurring for the nucleus being represented by that die, then lambda would be 1/6. You've got 1/6 chance. And then each time you roll it, that corresponds to 1 second, 1 unit time. The activity of a sample, that depends on how many undecayed nuclei you have. So activity, we denote with an A here. You've got not confuse that with nucleon number, and N being number of undecayed nuclei. You don't want that to confuse that with number of neutrons either. If you have more nuclei available to decay, then there's a higher, and each nucleus has the same probability of decaying, then there's a proportionally higher activity. Oh, sorry, I meant to point out the equation. The equation, activity is the probability, which is the decay constant, multiplied by the number of undecayed nuclei. Okay? Units of that are becquerels, which is in SI is seconds to the minus 1. Okay? Any questions about that?
So the definition of activity?
It's the number of decays that happen per unit time. Okay. So the activity is the number of decays per unit time. So the probability multiplied by each nucleus decaying in a unit time will give you that. Alright, exponential decay. Radioactive decay is exponential. This is radioactive decay looking at a sample where you have lots and lots of radioactive nuclei. Exponential means that there is a constant ratio property. So the same ratio will decay in the same time period. Activity is the number of nuclei that decay per unit time. So that's given by minus dn over dt. The d's indicate a small change in number of undecayed nuclei over a small change in time. Activity is decreasing because once a nucleus has decayed, according to a particular type of radioactive decay, then it can't decay again. Okay? For that reason, because the number of undecayed nuclei is decreasing, your activity is going to get smaller and therefore you have a negative there, you have a minus. I'm going to show you the derivation for the equation for the number of undecayed nuclei as a function of time, and you don't need to know this, but you can just see how it comes about. So A is lambda m, we just saw that, it's the probability multiplied by the number of undecayed nuclei, and then we'll just see this. So we can equate those two equations there. Now we're going to rearrange that so that we can then integrate it. So we've got our decay constant, note this is a constant, minus lambda there, and we've got dn over n. Now we're going to integrate, and we're going to integrate with limits. So we're starting at t0, which we'll call 0. And we're going to a time, some general time t. So that's our limits for the time. The corresponding amounts for n are at t0, we start off with n0. So that's our starting number of undecayed nuclei. And we go to some general value of n, which we'll call n. So we've got 0t and then n0 and n. Let's integrate those. So if we integrate this, we'll get t. So t at time t is t, and t at time 0 is 0. So we get minus lambda, because that didn't change because it's constant, multiplied by t minus 0. And then if we integrate 1 over n with respect to n, then we get log n, natural log, that is, ln. So we get log of n minus log of n0. Okay, so that's the integration. Let's rearrange that. So we get minus lambda t, because that 0 is just going to come out, is equal to log n minus log n0. And then use the log rule here, that's log n divided by n0. Rearrange again, and the inverse of a natural log is e to the power of the quantity within the log. So we now get n equals n0 e to the minus lambda t. And that's the equation. You need to know that equation, you need to use that equation, but you don't need to know how it's derived. Also, because a is equal to lambda n, so that's just a constant multiplied by n, then we can, the activity, the general activity, when you have n nuclei is A, and you start off with activity A0, so you can use this equation and substitute for A and A0 there, so you get A equals A0 e to the minus lambda t. Okay, right, what do you get when you plot a graph? And the constant ratio property for radioactivity is based upon 50%, which is the half-life. So that, I'll define half-life on the next slide. The equation, the graph rather, that you get, if we plot n against t, we start off at n0, and then it obeys this constant ratio property, so it's going to drop to 50% of n0 in some time, which for now we'll just call it the half-life, and I'll define it on the next slide. And then it will drop another 50%, but 50% of n0 over 2, so that's a half of a half, so that's n0 over 4 at 2t half, okay, which is 2 times the half-life. So you've got a common mistake here is people think once you get to 2 half-lives it will drop to 0, but that's not the case. It's because at this time you have n0 over 2, so it's going to drop to 50% of that. So that's half of a half. Right, definition then of the half-life is, which we call T half. That's the mean time for the number of undecayed nuclei to half. Now, again, you don't need to know this derivation, but you need to know how to use the equation. You need to know the equation and how to use it. At a half-life, we have n equals n0 over 2. Let's use this equation then that we just looked at. So substitute in for the values of n and t at the half-life. So we get, for n, we've got n0 over 2, and t is t half, right? So we put those values in, rearrange that, and we've got half is equal to e to the minus lambda t half, because the n0's cancel out. Take logs of both sides, so we get log of a half, and we've got minus lambda t half there, because log of the e is the inverse. And then rearrange that, we get log 2 is equal to is equal to lambda t half, the minuses come out. So if you take the minus np, you get log 2 rather than log half. So the half-life and the decay constant are related according to that equation. Half-life is equal to log 2 over lambda, and vice versa. Lambda is log 2 over t half. Log 2 to 3 significant figures is 0.693, so you can see it written in that form also. Okay, practical application then, carbon dating. Carbon-14 is a radioactive isotope of carbon, it's unstable. The isotope ratio in the atmosphere, carbon-14 to carbon-12, is about 1 to 10 to the 12. So, sorry? Is that the ratio?
Do you have to know that ratio?
No, I don't think you need to know that ratio, not off by heart. So it's very rare, but it's roughly constant, okay? So we can use that as a baseline. All living organisms maintain that ratio because they're constantly taking in fresh carbon during their life cycles, so they maintain that ratio. But as soon as organisms die, they stop taking in fresh carbon, so they start off with that ratio, but then that ratio will start to change because the carbon-14 will decay. What you can do is compare the sample activity of something that died a long time ago to that of a living sample, and that gives you a starting point. So you've got A, because you've got the present activity, but then you also have A0, or you have N, because you can work out how many undecayed nuclei there are in your sample, and you have N0 because you know how many you started off with. Okay? So you can look at it from A or A0 or N and N0. You also have to assume though that this ratio is not changing with time. And if it is changing, you need to factor that into your calculations. Okay. Carbon-14 is a beta minus emitter, and we know the half-life. So you've got 5,600 years for the half-life. And what that enables you to do is to work out how much time elapsed between now and when the organism died. Okay? So that's been used on various artifacts, including dead bodies that have been, human bodies that have been found in peat bogs and things like that. So they died a long time ago, and you can use it to work out within a margin of error how long ago it died. Okay, but usually it's hard to use this type of radioactive dating because you don't know how much you started off with. What's important about carbon dating is that it gives you a starting point. Okay? Alright, now let's have a look within the nucleus, and we're going to look at forces within the nucleus. We'll consider how this atomic nucleus is held together. Which force is responsible? What we're going to do is consider two protons, okay? Because they have a couple of forces that we already have experience with. So we've got two protons that are bound in the nucleus. The mean separation between the centres is 10 to the minus 15 metres. There are two forces acting on the proton that we know of. There are gravitational force, because they both have mass, so there's a gravitational force between them, and an electrostatic force, but because they have the same charge, it's repulsive. So we've got an attractive force and a repulsive force. Are those forces responsible for holding the protons at equilibrium within the nucleus? Let's bring in some data here. We know the charge on protons is plus 1.6 times 10 to the minus 19. We know the mass of protons is 1.67 times 10 to the minus 27 kgs. So what we can do now is we can apply Newton's law of gravitation. We find that the gravitational force is 1.86 times 10 to the minus 34 newtons. And Coulomb's law, to find out the electrostatic repulsion, has 230 newtons. And what you can see is that the electrostatic force is huge in comparison to the gravitational force. So there is no way those two forces are responsible for holding those two protons at equilibrium within the nucleus. And therefore, we know gravitational force alone is not responsible for holding the nucleus together, because this electrostatic force is trying to pull them apart. There must be another force which is attractive, and it's called the strong nuclear force. And that means with this and the weak force, we've now come across our four fundamental forces: the gravitational force, electromagnetic, the weak interaction, and the strong nuclear force. So we've got these four forces. Let's look at this strong nuclear force in a little more detail. It's a very short-range force, and so it only acts between neighbouring nucleons. So you need to have protons and neutrons very close. That's because it acts between quarks, so you need to have them very, very close together. If the nucleons are quite far apart, you know, larger than 10 to the minus 15 metres, then it's attractive, so that it can overcome the electrostatic repulsion between protons. At very, very short distances, so if you're getting less than 10 to the minus 15 metres, then it becomes repulsive as well, and that stops nucleons collapsing together. So that's how the strong nuclear force works. If you have very large nuclei, with like a nucleon number larger than 40, then you need more neutrons than protons, because what that does is it increases the average distance between the protons, and that decreases the electrostatic repulsion, enabling the strong nuclear force and the electrostatic force to be balanced. Once you start putting more and more protons in there, that electrostatic force will get very large. So So you need a way of balancing it out, and the way that that happens is by introducing more neutrons. So you can imagine it's like padding out that positive charge. So if you plot, this is the number of neutrons against the number of protons, then this dotted line here is where n equals z, and for stable isotopes, the line curves away from n equals z towards the end because you need more neutrons than protons. So that shows the trend of stable isotopes compared to the line where n equals z. So that's the strong nuclear force. Mass defect. Let's consider the constituents of the helium nucleus. We have 2 protons and 2 neutrons. When those 2 neutrons and 2 protons are bound in the helium nucleus, then the mass is 6.6467782 times 10 to the minus 27 kilograms. What happens if you split those up into 2 protons and 2 neutrons that are all separate? Well, the mass is 6.695104 times 10 to the minus 27 kilograms. You can see that those masses are not identical. The mass of the individual nucleons is larger than the mass of the combined nucleus. So there's a difference in mass, which is 0.048322 times 10 to the minus 27 kilograms, and that difference in mass is called the mass defect. Related to that is another quantity called the binding energy. Where did the mass go? When the nucleus is split up, it gained mass. When it's combined, it lost mass. So if you combine them, where did the mass go? Where it went was it was converted into energy. And now Einstein showed that mass and energy coexist, so mass energy is conserved. According to this relationship, delta E, binding energy, is equal to the mass defect, which is delta M, multiplied by c squared. Okay, so when you bring your nucleons close together, if you get in the range over which the strong nuclear force acts, then it takes over to bind the nucleons together. And there's a loss in mass because energy is released. And if you want to separate out those nucleons, then you have to do work against the strong nuclear force. You've got to overcome it, and that means there's a gain in mass because you've supplied energy into the situation. So you've given those particles energy to overcome the strong nuclear force, so there's a gain in mass. You can then, using this equation, calculate the binding energy for the helium nucleus using the mass defect. So that tiny amount of mass multiplied by c squared gives us 4.34 times 10 to the minus 12 joules, okay? Which is a small amount of energy, yes, but it's a very small nucleus. So you actually, for a small amount of mass, get quite a lot of energy because of this c squared multiplier. Yeah. Alright, so that's what the binding energy is. And I'll show you how it's plotted as binding energy per nucleon against nucleon number. So we normally plot the graph this way around. This is your binding energy per nucleon. That means, you know, for the helium nucleus, you've got 4 nucleons there, so it's total binding energy divided by 4. There is actually a spike here, which is due to the helium nucleus, because the helium nucleus is very tightly bound. A is your nucleon number. The most tightly bound nucleus is iron 56. Okay? So that's at the lowest point on this graph, so it's got the highest binding energy per nucleon. And this graph helps us understand the principles of fusion and fission. On the left of this graph, we can see that if we were able to fuse nuclei together so that they got larger but were moving towards iron 56, then we could get an output of energy. Okay? And if we were able to split up, fission, very large nuclei, so that they were, again, the products of that reaction were closer to iron 56, then again we would get a net output of energy. So let's look at each of those procedures in more detail. Look at nuclear fission first. The first thing to understand with fission is that atomic nuclei are dynamic structures. They're constantly changing shape. Okay, so they're not like a static sphere that don't move at all. They're constantly changing shape. Some, not all, very large nuclei are fissile, and that means that they can split into very large fragments plus some neutrons. Okay, so when it splits into two large fragments, there are some neutrons with it as well. This is not alpha, beta, or gamma decay. This is a completely different thing. Okay. When this happens, what's happened to the actual nucleus is it's become so elongated. Remember that the whole nucleus is filled with protons, so it's all positively charged. If it becomes so elongated that this electrostatic repulsion becomes considerable and can overcome that strong nuclear force in the middle that's holding the two bits together, then it can break apart. So if that electrostatic repulsion becomes significant compared to the strong nuclear force. The process, though, is not normally spontaneous. You usually have to force this one to happen by firing a neutron into the fissile nucleus. Okay, so what happens is there's our fissile nucleus. We fire a neutron into it and it splits into two large fragments and some neutrons. Because this process results in a net loss of mass, then energy is released, and it's released in the form of kinetic energy. And an example reaction here using uranium-235 is that uranium-235 plus our neutron will be fired into the nucleus and turn into barium and krypton and two neutrons. Okay. Hopefully my numbers add up. Should do. Okay. So that's looking at one nucleus. You can obviously have lots of nuclei that are fissile all together. And if you get these neutrons out here, what if those neutrons went on to cause further fissions? And that's called a chain reaction. So in a chain reaction, you start off with lots of uranium-235 nuclei, for example, because it's a fissile nucleus. If the neutrons from one can go on to induce further, then because you're getting 2 or 3 neutrons produced, you're producing more and more reactions every time, at every stage. So you can get more and more reactions taking place, and because you've got an output of energy, you can get a lot of energy output. If it's uncontrolled, then you get an explosion. Okay, so we just got 2 neutrons, they went into these 2 nuclei here, and then we got 2 from that one and 2 from that one, so they caused these ones to react as well. So if that reaction is unchecked, because you've got this exponential, certainly at the early stages, and then it may become less than exponential but continue to increase, then you can get an explosive output of energy. And that's the principle of how the atomic bomb works. So the atomic bomb uses an explosive chain reaction to get its explosion. You don't really need to know for exams how you construct an atomic bomb. Just giving you an idea of how it is done. Naturally occurring uranium is predominantly uranium-238, and that's not fissile. So 99%, just over 99% of uranium is uranium-238. What you need for an atomic bomb is 90% uranium-235. So you have to go through some very dangerous and very difficult procedures to get your enriched uranium. And then you need to achieve critical mass as well by compressing the uranium core, increasing its density, so that the neutrons that are released in each fission can then induce further fissions, because just at its normal density that won't happen. Those neutrons can't cause further fissions. The way that critical mass is achieved is you take a uranium core, you surround it with shaped explosives which will explode inwards. So you implode that uranium core down to just the right amount, so it's at the critical mass, so you've exploded it inwards, and then at the critical mass, some stray neutron will set off one reaction, and then you'll get your explosive chain reaction. So that's how the chain reaction is achieved with an atomic bomb, but that's for destructive purposes. Now let's look at non-destructive purposes, which is for fission in a reactor. If you're building a power station which you want to generate electricity from over a long period of time, then obviously you want to make sure you're controlling your chain reaction. You don't want an explosion taking place. And when you do have an explosion taking place, like in Chernobyl, Fukushima, that's bad time, so you don't want that to happen. So how is it done? There are three components that you do need to know about, and how this fission reactor works in broad strokes, you do need to know and be able to explain. You have fuel rods, that's where your uranium is. Now, unlike the weapons grade uranium, where you needed 90% uranium-235, here you need only 3 to 4%. Okay? So those dangerous and difficult to achieve procedures to enrich uranium are on a completely different scale for weapons grade uranium as with civil uranium. So that contains your 3 to 4% enriched uranium-235, or uranium. You've got a moderator, which is often graphite, and then you have control rods, which are made out of some material such as boron. This is a schematic diagram. These gold rods here, those are our uranium rods. Okay, so that contains our uranium. That's where our reactions are going to take place. They're going to get hot there. The neutrons that come out of a fission are moving too fast in order to induce further fissions. So what we need to do is slow them down. We use graphite to do that. So the neutrons will bounce off of the carbon nuclei in the graphite. They're not physically touching, just the electrostatic repulsion. Sorry, yeah, they're getting very close, yeah, because they're not positively charged. So they're bouncing off the carbon nuclei, and that slows them down because the carbon nucleus will recoil, so some of the momentum is gained by the carbon nucleus. That slows them down. They can then induce further fissions in the uranium, and the uranium gets hot because of this energy release. You have a heat exchanger, might be using something like carbon dioxide to pump it around here into this heat exchanger. So you use the carbon dioxide as a coolant to cool down the reactor core. That's then heat exchanged with the water, turns it into superheated steam, drives the turbine. In order to control the rate of reaction, then you use control rods, and they can be raised or lowered. When they're raised, you speed up the reaction because boron absorbs neutrons. So if you take the control rods out more or completely out, then all the neutrons released will induce, nearly all of them will induce further fissions. If you lower them, then you absorb more neutrons, and that prevents or reduces the number of reactions that take place per unit time. Okay, it's the rate of reactions you need to refer to, not just the number of reactions, because over a long period of time you can get a large number of reactions take place anyway, whether the rate is high or low. So it's the rate of reactions you control with the control rods. And that's a fission reactor. As I said, that's the heat exchanger, which is then producing the superheated steam. Nuclear fusion, that occurs in nature, in the core of stars, where the stars fuse predominantly hydrogen into helium. Under certain conditions they can fuse larger nuclei as well. You need extremely high temperatures in order to get fusion done on a large scale, like 10 to the 9 Kelvin. And the reason for that, is that your reactants, like hydrogen, they need to have sufficient kinetic energy to overcome the electrostatic repulsion, to get those nuclei close enough together so that the strong nuclear force can take over and fuse the nuclei together to form helium, for example. However, you can get some fusion occur at lower temperatures, and the reason for that is that the hydrogen nuclei in your reactants, that they don't all have exactly the same speed, they have a range of speeds, and some of them will have sufficient kinetic energy to fuse. So you can get small amounts of fusion even if you don't get to the temperature where you can get substantial fusion to occur. So fusion occurs naturally in stars. Fusion has been achieved to produce explosives, so we have hydrogen bonds, they fuse hydrogen and you get an explosive output of power. There is also a lot of work being done to try and achieve fusion on an economical scale where you can get a large output of energy. It should be achievable, but it hasn't been achieved yet. One of the projects that is closest is the one taking place at the National Ignition Facility over in California. They're using lasers to bombard small amounts of fuel, giving the fuel sufficient energy to fuse. And they actually managed to get more energy output than what they put in for a short period of time. So it wasn't done on a large scale yet because it's still a scientific project rather than a practical engineering achieved reality. So they are very close, but when it actually becomes put on the national grid, who knows? This is an example of the fusion of deuterium, which is an isotope of hydrogen, 1 proton, 1 neutron, and tritium, which is another isotope of hydrogen with 1 proton and 2 neutrons. So it fuses into helium and we get a neutron ejected. Again, you get a net loss of mass, giving us energy release, and it's that energy that we want to use to drive our turbines. The reaction as an equation is here, so that's an example of fusion. And that brings us to the end of nuclear physics. Hope that was useful. All right.